My name is Judy Mizraki. In case if you have not seen my other videos, Judy Mizraki. Okay, and this is EL6303, and I'm doing homework 2. This is problem 2, okay? So, I really like this problem, actually. It kind of looks icky, but it's really not too bad, really, because it's kind of pretty functions. So, the first one, it tells us to, I'm doing number 2, it says to draw f of x equals 1 minus e to the minus alpha x times u of x minus c. And this is really actually pretty easy because u is just the unit step function, which is u of x equals 1 when x is bigger than 0, and 0 when x is less than 0. Okay, that's u of x, so of course it's x minus c. So if we want to draw it, that's pretty easy. This is just going to be an inverse exponential, like starting with from 1, and this is going to be this is going to shift the whole thing because basically we're cutting out everything until c, right? This is the x-axis and this is the f of x. And so we're going to bring it up a bit here, and it's going to look something like this. If you can, it's not the best drawing, but you kind of get the idea. And this is going to be 1 minus e to the minus alpha x, and of course it just cuts off here because all this effectively does is say that this function is only valid when x is bigger than c. Okay? Awesome! Awesome. Now, you want me to tell you, is f of x a valid probability distribution function? And the answer is yes. Why? I mean, it's kind of obvious that it is. First of all, because it satisfies the property that, x is always kind of getting, well, I'm trying to think of a good way to explain it. First of all, the simple answer is that it satisfies all the properties of being a valid probability distribution function. Also, all the x's, like as you get bigger, it works, and as you get smaller, it doesn't work. So if you get below a certain amount, right, then anything below that gets cut off and it doesn't work anymore. And it's kind of sort of a way that I like to think of what it means to be a probability distribution function. Like it starts somewhere and then it's continuous. But just generally thinking, you can just kind of look through the 8 properties in the book and it does satisfy everything. Like, for example, the easy one, right, that check it out, when x, what happens as x approaches infinity, right? Well, if it's valid, then this means that it should approach 1. Let's see if that works. So we get 1 minus negative infinity, this is 0, times the unit step function, of course, this is bigger than 0, so this is going to be 1, is going to equal 1, so we're good. What about at negative infinity? We'll see this, negative infinity. We should get 0. Let's see if we get 0. This is some 1 minus e to the minus, we'll say, approaching negative infinity. It's not really possible to get there. But so we're not going to deal with this yet because we don't have to, because this is going to be something much, much less than 0, right? So the whole thing is going to be 0. So we're good. Okay, and if you check all the properties like that, you're going to find the same thing. So yes, 'tis a valid distribution. Beautiful. Function. Awesome. Okay, good. Now we're going to do the next step. Can you still see that? Okay, good. Where we want to find f of x. Okay, now recall f of x is just we just differentiate big f of x. Now this is kind of an easy differentiation. We're just taking this is f of x is this. Let's see the top part. Oh, we can't see it anymore, that part. So I'm just going to rewrite it down here. So you see we're taking d dx of 1 minus e to the negative alpha x times the unit step function, that's c. Okay. Now recall, before we even start, the derivative of the unit step function is just a delta function. So we're going to do the first times the second, plus the second times the first. Remember that, how that goes? Times the derivative of the first, whatever, blah, blah, blah. So the derivative of this part is just 0 plus, now, of course, we can differentiate this. So we're going to get alpha e to the minus alpha x for the first part, and of course times the unit step function, because this is the part we're not differentiating, plus the derivative of the second times the first, so that's just going to be the Dirac delta function at c, times the same original thing. Does that look good? Yes. Okay, just take a minute and just make sure that makes sense to you. Do it in your head. Take the differentiation and make sure you're happy with it. Okay, awesome. Now, of course, we can't just leave this like this. because if we try to graph this, we're going to get ickiness. But fortunately for us, we can make a little change, because remember, the sampling property means that we can take this x here and replace it with a c, because this is an impulse function, right? Because the Dirac delta function, of course, looks something like this: 0, 0, 0, 0, infinity, right? 0, 0, 0, 0, 0. So what this is just giving us is a value at this one impulse, right? So that only is going to mean anything at all. This is equal to 0, okay? Unless if, this is equal to, or 1, I guess, unless if this, or 0, I'm sorry, because this is going to equal 0, and except for when x equals c. Okay, so we can replace this by c. So this is the same thing as saying alpha e to the minus alpha x times, again, the unit stem function, plus, we can just leave the delta function in there, because, like, why not, times 1 minus e to the minus alpha c. Okay, and this is your answer. Okay, now, should we graph that? We'll graph that. And we get, it's going to look something like this. So we have f of x, and of course, again, it's shifted to c. Okay, and it's going to start, we'll make it start around here, and it's just going to look like an exponential. So it's going to kind of do this kind of a thing. And of course, we know that the area of this, right, because how this works over here, is going to be 1 minus e to the minus alpha c. And the reason for that really is because when you integrate this, you get bada bing, bada boom, this. And the integral of a function is just the area under the curve. Okay, so I hope you enjoyed that. Thank you for watching, and you will see me again, I think, by problem 5. All right, bye-bye.